My name is Mikkel Peters, and this is Lab 4, Oscillations. The purpose of this lab was to analyze the motion of a mass spring system where the mass travels in an oscillating arc while on the spring. A computational model was created in GlowScript to create a graph of predicted versus actual motion. This lab was based on the energy principle as well as Newton's second law and the momentum principle. In this lab, the system includes the spring, mass, and earth, and there is nothing in the surroundings, which according to the energy principle means that work is equal to zero because nothing is there to exert work on the system. As a preview of the results, the predicted motion aligned with the experimental data with the exception of small deviations in both the x and y directions. Underlying fundamental physics formulas and principles that are relevant to this lab include the velocity update formula, position update formula, spring potential energy, gravitational potential energy, kinetic energy, and the energy principle. The first two are based on Newton's second law, while the last few are based on the energy principle seen here at the bottom. Initial conditions. This first section here shows constants that we know such as k, L0, and g. This second section shows the initial position and velocity of the spring calculated from the video. The final section defines and calculates the initial energies. For the tracker analysis, the relaxed length of the spring, 0.7 meters, was used to calibrate the program. This was from the pre-lecture videos found on Canvas. Point mass was used to capture the motion during each frame, seen here, and data was exported as a .csv file to extract the x and y data to input into the GlowScript code. This first section of the code sets up the initial conditions. Values for L0 and K were taken from the pre-lecture videos, and the initial state, including spring potential energy, gravitational energy, total energy, and kinetic energy, are all calculated. And these calculations are based on the formula shown at the beginning of this presentation. This is the calculation loop of the code. Here, we start by defining the energies of the system, such as kinetic energy, spring potential energy, gravitational potential energy, and total energy. We then calculate the forces which contribute to the net force, which is the spring force and the gravitational force. We then use the momentum principle to update the position and velocity, as well as L, the length of the spring, and S, which is the change in L0 and L. We finally calculate the change in energies, both potentials, gravitational and spring, kinetic, and total, in this section here. After we ran our code, we were left with this graph right here, which is the change in energy versus change in time. This blue line here shows the change in kinetic energy. The red line is the change in gravitational potential energy. Green is the change in potential spring energy, and orange is the total energy. We can see that the orange stays at 0 throughout the entire simulation. Since there's no surroundings, there's no work. Therefore, since work is the capacity to change the energy, total energy stays at 0. Finally, once we had our results, we were able to compare the two models. This top graph here shows the x position of the mass versus time. The blue is the simulation and red is experimental data. The model is consistently more positive, therefore shifted more to the right, than the actual data. And this bottom is the y position versus time. Once again, blue is the simulation and red is experimental. And throughout the run, the model is consistently higher than the actual data. This can be contributed to the simulation not considering the mass of the spring, which in real life does contribute to the position of the mass. Results. Overall, the results do match the expected simulation and are consistent with Newton's second law and the energy principle. Possible sources of error may include not consistently tracking the point mass in the center of the spring in the video, which can cause errors in the position versus time, and potential calculation errors for constants and for changing values. Our first what does it mean question asks if the energy principle is satisfied, and to justify our answer using the energy plot. Yes, this is satisfied in this model system, and that is evidenced by delta E staying 0 throughout the simulation because no work is done. Finally, we are asked to calculate the two oscillation periods for the x and y. For x, it is 1.633 seconds, whereas for the y, it is 1.520 seconds. And this could be due to traveling different distances in each direction, as the mass was not released at a perfect 45-degree angle.